This is Vodcast 11B. We're going to start off this video by reviewing what we did in A and calculate some more concentration. Number 1, my solution is prepared by mixing 1 gram of ethanol with 100 grams of water to give a final volume of 101 milliliters. Calculate the molarity. I don't know big M. Molarity equals moles over liters. I don't quite have either of these. I don't have moles and I don't have liters. Can I figure out my moles? I'll have to do one little calculation. 1 gram of ethanol, here's your formula. How would I convert that into moles? 1 mole is equal to, I need to look up on the periodic table, adding together 2 carbons, 6 hydrogens, and an oxygen. The mass should be 45.07 grams. 1 divided by 45.07 grams, with my grams canceling, converts me into moles of ethanol, which is 0.0222 moles. That goes into my concentration equation, 0.0222 moles, divided by liters. Again, I don't quite have liters because I have milliliters. If you take milliliters and you divide by 1,000, or you move the decimal point 3 places, you can convert into liters. 0.101 liters. Now I have moles and I have liters. I simply divide and I get 0.220 molar solution. Number 2, what's the chemical formula for nickel 2 sulfate? Nickel 2 plus sulfate. If you don't remember it, look it up. SO4 2 minus. Chemical formula is NiSO. Now that I know my formula, what is the concentration? Concentration again means I'm solving for big M. Moles over liter. Concentration of a solution with a volume of 500 milliliters. Convert that to liters. Move the decimal 3 places or divide by 1,000. 0.5 liters. That contains 32.9 grams. One little snowman calculation, grams to moles. Looking up the mass for this guy, calculate those from the periodic table. I got 154.76 grams. Divide, grams cancel, converting into moles should be 0.213 moles of nickel sulfate. Putting 0.213 moles into my equation, 0.213 divided by 0.5, 0.425 molar as my final calculation. Okay, now that we know how to calculate concentration, we're going to add just a little twist. Calculating that concentration is my standard solution. It's the one that you start with, the one where the concentration is accurately known, and if you add more standard solution to standard solution, you don't change your concentration at all. The volume would change, but the moles would also change, so your concentration stays the same. If I were to add water, think if you have your favorite Gatorade or your favorite some kind of juice. If you add water to it, what happens? It gets diluted. Adding water dilutes a solution. The volume increases, but the moles stay the same, so my concentration has to go down. When you add water, you dilute your solution, concentration goes down. Here's the calculation that we're going to use. This equation should look similar to you. It's in the same format as one of the gas law equations, where M1 stands for the initial concentration. V1 is how much of that standard solution do we use. M2 is my final concentration. Again, always lower than initial. And V2 is our final volume. So let's try some of these. A solution is prepared by dissolving 10.8 grams of ammonium sulfate, here's the molar mass, in enough water to make a 100 milliliter standard solution. So first I have to calculate my M1. M1 equals, I need to get this into moles. 1 mole, 132.41 grams. How many moles of ammonium sulfate do I have? 0.0816 moles. 0.0816 moles divided by, again, converting to liters, 0.1 liters, you should get a concentration of 0.816 molar. 0.816 is my M1. Now, for the dilution part, here's where it changes. This is now when we're going to use M1V1 equals M2V2. I know my M1, 0.816. My V1, a 10 milliliter sample of the standard solution, 10 milliliters, 0.01 liters, is equal to M2. What is the molarity of the new solution? I don't know M2. Times, what's my V2? I'm taking 10 milliliters and I'm adding it to another 10 milliliters of water. So my final volume, 10 plus 10, or 0.02 liters. Dividing both sides by 0.02. Liters cancel. My units are going to be in molarity. That's what I want. I want M2. Punch that in your calculator. M2 comes out to be 0.406. M2, always less than M1, because I'm diluting, I'm adding water, it's becoming less concentrated. Another problem. Calculate the concentration of sodium carbonate. Here's my molar mass. When 10 milliliters of a 3 molar solution is added to 40 milliliters of water. Here's my equation. Let's figure out what am I given. Calculate the concentration of sodium carbonate. That sounds like I don't know M2. When 10 milliliters, that would be my V1, of a 3 molar solution, that's my M1, so 3.0 M times 10 milliliters, convert that to liters, equals, I don't know M2, times, I'm adding 10 milliliters to 40 milliliters of water, 10 plus 40, my final volume, 0.05 liters. Again, solving for M2, divide both sides by 0.05. Liters is going to cancel. My units will be in molarity. When you plug this into your calculator, you should get 0.6 as M2. Is M2 less than M1? Absolutely. Always M2 must be less than M1 when you're diluting because you're adding water. Part 2 of this problem. How much water must be added to a 25 milliliter sample of the original solution? My original solution was up here, 3 molar. 3 molar. I'm adding it to 25 milliliters, or 0.025 liters. To make the molarity, the final molarity, I know this is M2 because this is less than M1, and I don't know my final volume. I need to figure out how much water to add. So this time, solving for V2, dividing both sides by 1.25 M, molarity cancels. My units are going to be in liters. I punch this in my calculator, and I get V2 equal to 60 milliliters. That's my final volume. But be careful which way the question is worded. It says, how much water must be added? I started with 25 milliliters. My final volume has to get to 60. So 60 minus 25. How much water has to be added? If I'm using 25 milliliters of my standard solution, I need to add 35 milliliters of water to get it up to the 60 total final volume mark. Just be careful how the question is worded. So what is solubility? Here's your definition. It's the maximum amount of a chemical that will dissolve in a specific amount of solvent at any given temperature. For solids, if it's soluble, it will dissolve. Remember we said likes dissolve like. Polar and ionic things will be soluble in water because water is also polar. If they do not dissolve, they are said to be insoluble. For liquids, slightly different terminology. If two liquids mix to form a solution, they are said to be miscible. If two liquids dissolve in each other, they're miscible. If they do not form a solution, like oil and water, they have layers, they don't dissolve in one another, they are said to be immiscible. They won't dissolve, they'll be not homogeneous, they'll be heterogeneous. So what affects solubility? 3 things affect solubility: temperature, size, and polarity. We already talked about polarity. Likes dissolve likes. Polar will dissolve polar. Non-polar dissolves non-polar. Let's talk about temperature. If the process is endothermic, heat will increase the solubility. If your process is exothermic, heat will decrease your solubility. We'll get into this again in a later slide. And size affects solubility. It's easier to dissolve smaller molecules than it is to dissolve bigger molecules. Usually the larger the molecule, the less soluble it is. Here's a graph that shows us this temperature thing. This is for solids. Most solids, as you can see from this graph, temperatures in degrees Celsius, it goes from 0 to 100. And this is solubility. How many grams can I dissolve in 100 milliliters of water? You can see the general trend. Here's sugar. As I increase the temperature, the amount of sugar will change 40 grams to over 140 grams. You can dissolve more sugar if you increase the temperature. If you've ever made homemade sweet tea, you increase the temperature of the water so you can dissolve more sugar when you put the tea bags in. This is why. You can dissolve more sugar at a higher temperature than if it was ice water. We'll look at another one. This is sodium nitrate. All of these general trends. Here's table salt. Table salt only has a slight increase as you increase the temperature. But as you can see, for the exception of this one thing, the higher the temperature, the more solute you will be able to dissolve. Gases can also dissolve in water. That's how fish breathe, dissolved oxygen. Temperature does affect that as well. If you increase the temperature of your water, you actually decrease, these are inversely related, gas solubility. So if you want your fish to live longer, you probably don't want to heat up its water, because as you heat up the water, those molecules of oxygen inside the water want to move faster, and they actually escape and they come out into the air, into the atmosphere. We can also talk about pressure. Pressure has a very little effect on the solubility of liquids and solids because they're not able to be compressed. But pressure does affect gases. If you increase the amount of pressure of a gas, you can force more of it to be dissolved into the liquid. And the last thing we're going to talk about are precipitation reactions with solutions. These are all double displacement reactions. When you mix two ionic solutions together, sometimes you get a precipitate. If it's insoluble, you will get a precipitate. If they're both soluble, they'll all just dissolve. We're going to have to use something called the solubility rules, and they're located on your periodic table on the same page as your ions and the activity series. Here are the solubility rules that you'll find on your periodic table. We'll be referring to this a lot, so keep this handy or grab your periodic table. We're going to write balanced equations for the following. I will do the odds, and you can try the evens. Calcium hydroxide. Now we need our ions. Calcium, 2+, hydroxide, 1-, CaOH2, that's a solution. AQ, it's dissolved in water. Reacts with phosphoric acid, goes back to phosphate, PO4 3-. How do I get an acid? H+. Balancing that out, H3PO4, again that's a solution, AQ. Now, what happens in a double displacement? The calcium switches places with the hydrogen. So, in my product side, I have calcium switching with the hydrogen, so calcium goes with phosphate. Again, watch your charges. Calcium is a 2+, swap and drop. Phosphate is a 3-, so it's Ca3, PO4 2, and the H now goes with the OH. HOH is water. We know water to be a liquid, so for this one, the only one we have to look up on that chart is calcium phosphate. Going back to the chart, phosphates. Carbonates, chromates, oxalates, and phosphates are insoluble. That means it will form a solid. So calcium phosphate is going to be a solid. Why, since it said phosphates are always a solid, did it not form a solid here? This said it was a solution. If you go back, alkali metals, or anything in that first column, are always soluble. So hydrogen, since it's also in that first column, will also apply to this rule. It will be considered an alkali metal for this rule. It's always soluble. No matter what you put hydrogen with, it will always dissolve. So when you have this discrepancy where one is saying soluble and one is saying insoluble, always tend toward the soluble. If either one says soluble, make it an AQ. It'll be a solution. It will dissolve. And I'll do one more. Number 3. Before I do my next one, you have to make sure this equation is balanced. I have 3 calciums on this side, so I'm going to need 3 calciums over here. I have 2 phosphate groups on this side. I'm going to need a 2 here. That gives me a total of 6 hydrogen plus another 6 hydrogen. That's 12. So if I put a 6 out front here, 6 times 2 is 12. I now have 6 oxygen, and now I'm balanced. So I'll do number 3 for you as well. Aqueous solutions of sodium chloride. That's easy. We know table salt. We've dealt with that compound a lot. And ammonium phosphate. Ammonium. NH4 is a 1+. Phosphate. PO4 is a 3-. So it's NH4. Swap and drop. I need 3 of them for each PO4. Double displacement, double swap, switch sodium and ammonium. My sodium is going to go with the PO4. Again, swap and drop because it's a -3 and a +1. Na3PO4. And now my ammonium is going to go with the chloride. NH4 is a 1+, chlorine is a 1-, so they just balance out. Now I have to look back at my chart. Sodium and phosphate. Oops. Sodium is an alkali metal, and it says that alkali metals are always soluble. So this is AQ. It will dissolve. And ammonium chloride. Here's chloride. Chlorides are soluble except with, that's not ammonium, so chloride is soluble as well as ammonium. Both soluble. So they're both aqueous solutions. Again, I have to balance. 3 sodiums over here because I have 3 over here. 3 ammoniums here. 3 there. That's 3 chlorine. And now I should be balanced. Pause the video here and try number 2 and 4. I'll write out the answers so you can double check your work. Here are the answers for number 2 and 4, completely balanced with the appropriate states. If you got both of these correct and you feel confident, you may skip this next part. If you think you need some more review, here are lots more practice problems for you. We'll also be practicing this on some of the worksheets. Our very last topic in this unit is colligative properties. These are properties of a solution that depend on how many, the number of solute particles that are present. It doesn't matter what type you have, it doesn't matter what you have dissolved in your solution, it just matters how much you have. There are 3. Freezing point. It's called freezing point depression because as you add more and more solute particles, the freezing point is actually decreasing. The second one is boiling point elevation because as you add more and more solute particles, the boiling point is increased. And vapor pressure, if you add more and more particles, your vapor pressure goes down as well. How does this happen and why? Let's talk about freezing point. It only matters how much stuff you have. It does not depend what type. So, if I'm trying to freeze the solute particles, say I have water. If I have table salt dissolved in water, all those sodium and chlorine particles interfere with how water needs to organize itself to freeze. So if you add salt to water, you lower the freezing point. This is super helpful in the wintertime. Can you think of what I'm talking about? Your example, when they put salt on the roads, what does it do? It actually melts the ice because it's taking the freezing point from regular 0 degrees Celsius down to a negative. So depending on the weather, if it's at that freezing point, they can treat the roads with some salt. It actually lowers the freezing point. So the water won't freeze at 0 anymore. It'll freeze a little bit lower. How about boiling point? Boiling point actually increases. Why would I add salt to water to increase my boiling point? Let's think if you're cooking, specifically if you're cooking noodles, and you put some salt in the water, instead of boiling at 100 degrees Celsius, it might boil at 101, 102, 103. It may take a little bit longer to heat up, but once you put your noodles in, they'll probably cook a little bit faster. Here's a picture for you. Here's pure solvent. This could be pure water. And as you can see, when you add solute, so maybe this is table salt, maybe this is sugar, again, it doesn't matter what it is. It just depends on how much. If I'm trying to boil this, or if I want to look at the vapor pressure, these red guys seem to get in the way of the fact that the blue ones want to leave. So it interferes with the ability of the solvent to change from the liquid to the gas phase. So it changes the vapor pressure, it increases the vapor pressure, and it increases the boiling point as well. You have to heat it up to a hotter temperature in order to get those particles moving fast enough so that they can escape from the liquid to the gas phase. Here's what it would look like on one of our phase diagrams. This is the vapor pressure of the pure solvent. And what actually happens is it just widens the graph. Instead of 1 atm, right, that's my normal pressure. This would be my melting point, because this is my solid, again, liquid, gas phase. So when does the solid change to a liquid, my normal melting point, what actually happens to it? The melting point decreases to some lower temperature, and as your graph widens, the boiling point increases from, again, if this was water, this would be 100 degrees Celsius. The boiling point actually increases to a higher temperature in the solution, just because your solute has been added to the solvent. It totally widens the whole entire graph. It would change the triple point as well. So here's a sample quiz or test problem. Because colligative properties are additive, it doesn't matter what type of particle you have, it depends on how many particles you have. It depends on the number of particles. Which of these substances, A, potassium sulfate, B, sugar, or C, magnesium phosphate, would have a greater effect on these colligative properties? Which one would widen that graph the most? Potassium sulfate, K is a 1 plus, SO4 is a 2 minus. My formula would be K2, SO4. K2SO4, when dissolved, would break up into 2 K particles, 2 cations, plus 1 anion of SO4. It would break up into 3 ions. Sugar's not ionic, so sugar wouldn't break up at all. It would only have one type of particle. but magnesium 2+, phosphate 3-. Magnesium phosphate's formula would be Mg3 PO4 2. When magnesium phosphate would dissolve, I would end up with 3 different magnesium ions plus 2 different phosphate ions, for a total of 5 different ions dissolved in there. If you think back to that picture where it was all blue on the left, and then when you added some solute to your solvent and had those red dots, there would be 5 red dots as compared to 1 or 3 for each molecule that you add. So the one that would have the most effect would be the one with the most ions or the most particles that it would break up into when it dissolves. Magnesium phosphate. There are actual equations for the change in temperature, for how much the boiling point would go up and how much the melting point would go down, or the freezing point would go down, but we're not going to use those. I just wanted to show you in case you want to take honors chemistry or AP chemistry. We need to know just the fact that the boiling point is elevated. It actually goes up when you add more and more solutes. The freezing point, and vapor pressure for that matter, go down when you add more and more solutes. It totally just widens that whole graph. Freezing point decreases, boiling point increases. And that's it for this unit. Go back, review video A, review this stuff in video B, write down any of your questions, check your worksheets, make sure you don't have any blanks in your notes, and let me know what questions you might have tomorrow.